So dear students, now we are starting this question number 3 from the exercise 5.1, and this question is examine the following functions for continuity, and part A is fx is equal to x minus 5, fx is equal to 1 by x minus 5, x not equal to 5 condition here, and fx is equal to this fx modulus functions. So for the continuity, how to define any continuity, on which point any function is continuous. So at first, importantly for you, a function is continuous at x is equal to a if limit x tends to a, function of fx is equal to function of a. So it is very important. Almost 90% questions will be solved by that. X tends to a. In some cases, we will take left hand limit and right hand limit. The main thing is limit x tends to a, f of x is equal to fa. If both things equal, we can say it is continuous. So there is no point given here to check the continuity. Our function is given function is fx is equal to x minus 5. So if there is no point, we can take any real number for ourselves. Suppose let x is equal to, we are taking any c, that is a real number. This belongs to a real number. Then we use this. Actually, it is the linear polynomial. Polynomial function is always continuous at each and every point. But how to show this? How to examine this? Let's see. Here, f of x is c is equal to c minus 5. We have checked like this function, and now limit x tends to c, because x is equal to c, function of x equal to, what is fx? Limit x tends to c, function is x minus 5, and for limit we put x tends to c, we can put here, so you are getting c minus 5. That means we can say here it is also c minus 5 on the point x is equal to c, and now the definition is at the point x is equal to a, limit x tends to a, fx is equal to fa. If x is equal to c, x tends to c, f of x is equal to f and fc. So c minus 5. That means therefore function is continuous. It is continuous for each and every real number. So it is part first. So this function is continuous at which point c, and this belongs to a real number. We write this number. It was a number b is, our function is fx equal to 1 by x minus 5, and one restriction is given here. X is not equal to 5. Why it is written here? Because if we put here x is equal to 5, now see here 1 upon x is 5, so 5 minus 5 becomes 0. That means it is not defined. Function doesn't exist here. So it is a restriction given here. X is not equal to 5, because at the point x is equal to 5, this function is not the continuous. So we cannot take this. So x is equal to c belongs to real number. Then first of all, we take f of c equal to 1 upon c minus 5. Then we find limit x tends to c, and our function is 1 upon x minus limit x tends to c, x tends to c, one by x minus 5 equal to x is c, so 1 by c minus 5. So you can see here it is 1 upon c minus 5, it is also 1 minus. So that means limit f of c equal to this limit x tends to fx. That means both are equal. That means a function, otherwise we can write like this: function fx is continuous, but for x belongs to real number, but not this 5. We should write like this answer, because for x is equal to 5 it is not defined, so fx is continuous for each and every numbers except this 5. So x belongs to R minus this 5. So it is answer of the part B. Now we see part C. Now this part C is function is fx is equal to x square minus 25 by x plus 5, and expression is here x doesn't equal to minus 5. Why this happened? If we put here minus 5, it becomes minus 5 plus 5, that becomes 0. That means it will be not defined. So for the value of minus 5, it is not defined. So at there is no point, so we are taking as C. This belongs to real number, and fx is equal to, first we solve this, f of a. If you take f of c equal to, here x is c square, it is minus 25, and x is c plus 5, and it may be written as c square minus 5 square. It is the formula of a square minus b square. C plus 5, so c plus 5 and c minus 5, c plus 5. You know better this a square minus b square. In the first bracket a plus b, in the second bracket a minus b. So this becomes cancelled. So f of c is getting c minus 5. This point we have found here. Now this limit, always we take this formula, limit x tends to if c, fx is equal to f of c, otherwise x tends to a, fx is equal to f. Now limit x tends to x equal to c, we have taken right that the function of fx equal to function is x limit x tends to c, x square minus 25 by x plus 5, just like as previous steps. X square minus a square, that means in the first bracket x plus 5, in the second bracket x minus 5 by x plus 5. That means this a square minus b square like the same. In the first bracket positive, second bracket negative, so it will be cancelled. So that means limit x tends to c, fx equal to, if we put in the place of x it is c, so it is c minus 5. So f of c is c minus 5. This and this limit also c minus 5. That means given function is continuous at x is equal to c, belongs to R, but where is not defined? Minus 5. So we will write like the answer. At this point x is equal to c, belongs to R, real, for each and every real numbers, but except x minus 5. So it's answer for the part C. Now we will do part D. Now part D is fx is equal to this modulus, and always modulus function is always continuous, but actually we should examine this linear polynomial, any type polynomial, linear, quadratic, cubic, or continuous identity function that is continuous. Modulus is always continuous. So at x is equal to c, modulus means if we put any negative number, you know this thing, if minus 5 in the modulus, it becomes positive. If already positive, it becomes positive. So it is the continuous function. At x is equal to c, f of c is equal to c minus 5. And next one, limit x tends to c, fx is equal to limit x tends to c, and function is x minus 5. So for limit x tends to c, approaches to c, it becomes c minus 5. That means, therefore, f of c is c minus 5, also c minus 5 in the modulus. That means fx is continuous. Now question number 4 is, prove that the function fx is equal to x to the power n is continuous at x is equal to n, where n is a positive integer. Function is given this, fx is equal to x to the power n, and we have to check we have to prove this at point x is equal to n. So given function fx is equal to x to the power n, and we have to check at x is equal to n, and n is a positive integer. So main thing of our limit is a function is continuous. Be careful about this, very important this. Always we check this. The function is continuous at point x is equal to a if limit x tends to a, f of x is equal to fa. So we use this limiting function f of x. So here is x is equal to n. First of all we check this f of a, that means f function x is n, and here x is also n. X is equal to n. In the place of x we put n. So what it is coming? N to the power n. Let's see once again. Our function is fx is equal to x to the power n, and we have to check at the point x is equal to n. That means f of n. F of, in the place of x putting n, here x is n, power is n. So it was f of n. And now limit, also limit x tends to n. This function is limit x tends to n. Function is x to the power n. So x tends to n, that means putting x is equal to n, n power n. So clearly here limit x tends to n, f of x is equal to f of n. Both are same. That means fx is, hence fx is continuous at this point x is equal to n. So it is very easy this. Always we check this. We take limit x tends to a, fx is equal to f of a, and the point x is equal to a. So it was question number 4 solution.